We're going to work through an example of finding the net electric field resulting from a series of charges. So superposition again. I've got 4 charges, 2 positive, 2 negative, arranged at corners of a square. The charges are either 2 microcoulomb or minus 2 microcoulomb, and an edge of the square is 2 millimeters. And we want to find the electric field here at the center of the square, point P. So we're going to use superposition. The electric field at point P is going to be the electric field caused by charge 1, plus the field caused by charge 2, plus the field caused by charge 3, plus the field caused by charge 4, all added together. And we can do that because the field caused by charge 1 has no influence to change the field caused by charge 2, and so forth. So that's what we mean by superposition. So we need to find the field caused by charge 1 at point P and add the field caused by charge 2 at point P plus the field caused by charge 3 at point P, and then our last charge. Okay. There's a lot of symmetry in the problem. The magnitude of the charges are all the same, 2 microcoulombs, and since I picked a point that's at the center of the square, all of the magnitudes of the electric fields have to be the same by symmetry. So the field caused by 1 is going to be just as strong as the field caused by 2, as the field caused by 3, as the field caused by 4. And again, that's just by symmetry. Now doing the superposition, I'm going to sketch out what all the field contributions look like. Charge 1 is going to make an electric field that points away from it because it's a positive charge. So there is E1. Charge 2 is going to make an electric field that points towards it because it is a negative charge, and those vectors should be just as long as one another. Charge 3 is going to make an electric field that points towards it because it's a negative charge. So there's E3, and charge 4 is going to make an electric field contribution that points away from it. So there is the electric field caused by charge 4. And all those vectors should be the same magnitude, even if I didn't draw them like super awesome. Now I want to add 4 vectors together. I'm going to arrange them all head to tail. So there's E2 plus E4. And then there's E1 plus E3. And their sum is going to span from the tail of the first vector to the head of the last vector. So that purple vector is going to be the electric field at the center of the square. And we can observe it is only going to have an x component. All of the y components are going to cancel out in pairs. So as much as E2 points up, E3 points down. As much as E4 points up, E1 points down. And all of the x components are equal to one another, and they all point in the same direction. They're all parallel to each other. So I can find just the x component of, say, E1, and then multiply that by 4. We're going to need to find how far it is from a corner of the square to the center of the square. So let me just draw out a little triangle quick. So if a whole edge is 2 millimeters, that means half of an edge is 1 millimeter. And so this hypotenuse is going to be √2 millimeters. And to just summarize what we observed from our drawing, y components cancel, and x components will add. So let's look at just the field E1 so we can figure out how to pick out its x component. So E1 is a vector, looks like that. It has an x component, E1 comma x. It has a y component, E1 comma y, and this is a 45-degree angle. So E1, its x component, is going to be E1 cosine 45 degrees, and it points along the x direction. And cosine of 45 is 1 over root 2. So I can just write this as the magnitude E1 over root 2 along the x direction. And just for completeness, the y component of E1 is going to be minus magnitude of E1 sine 45 degrees relative to the positive y hat direction. And we would write that out as minus E1 over root 2 y hat. And the sine of 45 degrees is also 1 over root 2. So we can answer this question, what's the electric field at the center of the square, by finding how big the x component of E1's field is and making that 4 times bigger. But we need to find this magnitude. So how strong is the field E1? So the electric field caused by a point charge, so the coupling constant K, magnitude of the charge over the distance squared, inverse square law for the electric field from a point charge. K 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. The charge's strength, 2 microcoulombs, 2 times 10 to the minus 6 coulombs. And the distance we had just found there. So it's going to be root 2 times 10 to the minus 3 meters, quantity squared. So in terms of numerical value, I'm going to have a 2 times 10 to the minus 6 in the numerator. Once I square this, it's also going to be 2 times 10 to the minus 6 in the denominator, so those cancel out. So I sort of pick this problem to have a cute value. So if I keep just 2 digits in this, the electric field strength caused by one of the charges is going to be 9.0 times 10 to the 9th newtons per coulomb. So I can take that result now. So that is how strong the field caused by charge 1 is. That's the same magnitude for all 4 of them. And now I can just plug in the net field is going to be 4 times bigger than the x component from one of them. So the electric field at point P is 4 times the electric field's x component from charge 1, and we just found that. That's going to be 4 times 9.0 times 10 to the 9th newtons per coulomb over root 2 for the cosine 45 along the x direction. And just cleaning that up a little bit, the electric field, the center of the square, is going to be 2.5 times 10 to the 10th units of electric field, Newton per Coulomb, and it points along the x direction at the center of the square. So that's that.